Chapter 4 From Batteries to Motors. In 1936, a porcelain clay pot was found in a village near Baghdad, Iraq. It was almost 2,000 years old. In it stood an iron rod wrapped in copper. The rod stuck out from the copper above the lip of the pot. The rod was sealed to the pot with a pitch, a sticky substance made from tar. Scientists believe it was a battery. It was probably used for electricity. Volta's battery. In 1800, Alessandro Volta stacked plates of zinc with plates of silver. It separated them with paper soaked in salt water. He attached this plate to a flat copper wire. Volta's device sent electricity through the wires. He became famous for creating the first battery. That is because we didn't know about the battery in Iraq. The Baghdad battery was probably made about 1,600 years before Volta's battery. Until Volta's battery, scientists only knew about static electricity. Static electricity produces a shock and then disappears. Volta's battery creates a stream or current of electricity. It didn't go away just as soon as it appeared. Scientists began wondering if we could use this steady power supply. Years later, Englishman Michael Faraday figured out a new use for electricity, moving things. Faraday, magnet and electricity. Faraday noticed that magnets and electricity works in a similar way. A magnet has a north and a south pole, similar to a battery, positives and negative ends. When a magnet is close to a paperclip, it turns the paperclip into another magnet. The paperclip poles line up with the magnets. Each north pole is attracted to the other south pole. If the paperclip could move through the magnets, it would be pulled in one end and pushed out the other. Like electricity, the force in a magnet seemed to move in one direction. Imagine linking many paper clips together into a wheel, then place a magnet in the center space of the wheelie circle. What happens to the wheel if you spin the magnet? The wheel spins. Spin the wheel, and what happens to the magnet? The magnet spins. Inside the metal, the electrons are attracted to the magnet. They move with the magnet. Faraday electric motor. Now hold the metal wheel still and spin the magnet. What happened to the electrons inside the wheel? They rush through the wheel. Electrons that move through metals are electricity. If the metal or the magnet is still, the electrons move. In 1831, Faraday put a magnet inside the coil of copper wires. The magnets move the coil and create electricity, demonstrating electromagnetic force. Faraday used electricity to move metal. He created the first electric motor. How does a motor work? Motor works in similar today. A coil of wire is placed between magnets. A power source, such as a battery, provides electricity to power the magnet. On one side, the magnet pulls the coil. On the other side, the magnet pushes it. The coil spins, turning electricity into motions. It spins a rod that is attached to the coil. A rod can move things, like blades on a fan. The electricity can send power to things, such as wheels on a toy car. Motors and power plants. Power plants are the opposite of motor. They turn motion into electricity. Water is heated into steams. Steam pushes through tubes to the big turbine. A rod with wheels or blades like those on a fan. The turbine connects to a big magnet inside a room aligned with metal coils. The steam hits the turbine blades with a force like wind. The turbine and magnet spins. The magnets generate electricity in the coils. Cables carry the electricity to homes and other buildings. Life with motors. Modern life would be difficult to imagine without electric motors. They are used in fans and heaters. They power refrigerators and dryers. They drive power drills. They pull passenger trains. Before Faraday's electric motor, people used steam engines for power. These were huge and difficult to manage. Faraday's invention changed the world. It brought machinery to everyday life. Chapter 5. Electric comes home. Before electricity could be sent to home, scientists have to solve a problem. Metal is not perfectly smooth. It has tiny flaws in it. As electrons move through metals in one direction, they bump into these flaws. They bounce against each other. This bouncing creates heat. It also sends electrons away. People were losing too much electricity. Scientists have to figure out how to stop too many electrons from bouncing away. In the late 1800s, inventors and engineer Nikola Tesla discovered a way to take low-voltage electricity and transform it into high-voltage electricity. Soon after, he solved the problem of moving electrons by using alternating current, AC. The alternating current sends electrons in one direction for a brief time, then in another. This helps electrons avoid bouncing around too much. Alternating current loses less electricity in power lines than direct currents do. Tesla's alternating current system allows power companies to send electricity over many miles in high-voltage current. At the end of these lines, the electricity can be transformed into low-voltage electricity. This gas power electricity can be sent short distance to buildings, street lamps, and homes. Power lines can carry electrons hundreds of miles to your bedroom. Then you can turn on your reading lights.